All right, everyone. So in this video, we're going to start talking about NMR spectroscopy, your nuclear magnetic resonance spectroscopy, okay, and talking about some of the basic concepts of it, as well as then chemical shifts and what that's referring to and why that's relevant. So NMR spectroscopy, what you're probing is the energy levels related with spin, right? The different energy levels depending on what your spin is in your molecule. Right now, typically those energy levels degenerate, and we'll talk about how one breaks that degeneracy and is able to probe those energy levels. Okay. And what we talk about in this video can be applied to EPR, or electron paramagnetic resonance, okay, which is looking at the spin states of the electrons versus the spin states of the nuclei, right? So NMR is looking at nuclear spins, right? EPR is looking at electron spins. So for your nuclear spins, right, the electron has a total spin of 1/2, right? Okay, but your nuclei can have a variety of spins, and it just depends on how many protons and neutrons are in that nuclei and how those spins, the protons and neutrons, kind of add together. Okay, but you'll get kind of right if you have an even number, odd, or things like that, right? You can get things like, so if you have even number of both neutrons and protons, your total spin of your nuclei is 0. So you're not going to be able to probe it using NMR, okay? But if you have two odd numbers of both neutrons and protons, then you'd have integer spins, and then if one's even, one's odd, you'll get 1/2 integer spins for your nuclei, okay? And then these values here, I here, this is like S that we're talking about for the electron, right? This is the total spin, so I here, right, is our total spin, okay? Right, and it's an angular momentum, right? Spin is a type of angular momentum, right? So the kind of value is related with that, right? Right, I squared, right? The spin energy, if you will, it's like I squared over 2. It's going to be confusing with 2 i's, right? But right, remember with our total orbital angular momentum, right? You had right, that L, absolute value of L was equal to the square root L times L plus 1 times h bar, right? And it's the same type of thing with I, where here we're just using a different integer or whatever, different not integer, but a different letter, right, to determine or to kind of specify what we're talking about here. So we're using I instead of L, right? Okay. And then we'll define m sub I here as, like we do in all cases, right, is the angular momentum around, say, the z-axis. Okay, so it's just the angular momentum around a specific axis, and it ranges from -I to I in integer steps. Okay. So how does NMR work? Well, NMR works by essentially putting your molecule into a magnetic field. Now, it's not just, right, actual NMR spectroscopy doesn't just apply as a constant external field, right? It potentially applies to variable fields and things like that in order to align your molecules. And then, and then once you know they're aligned, then you can kind of probe energies and other things like that. So there's some things that are done in NMR spectroscopy that are a lot more advanced and complicated than what we'll talk about here, okay? But roughly we can think of it as basically NMR spectroscopy, you're applying this external magnetic field. Well, that external magnetic field will interact with the spins of your electrons, okay? Right, because right, this angular momentum is of an electron, right, is related to its motion, and a moving charge generates a magnetic field. So the kind of magnetic field generated by this electron interacts with the external magnetic field, and that interaction energy is given by this equation here in the middle of the slide, right, where GI is just this nuclear factor. It's a constant. and it just kind of depends on the nucleus. Okay, mu n is called the nuclear magnetron constant. Okay, it's also again another just kind of constant. That one is constant for all nucleus. Okay, B naught, right, is your strength of your external magnetic field. And then m sub I is that quantum number, right? M sub I is again is our quantum number, right? That takes values of minus I, 0 up to positive I, right? Right, and so this external magnetic field, right? If I apply external magnetic field, say in the positive z direction, right? If my nuclear spin, right, is aligned in a positive z direction, that's going to be a favorable interaction, right? But if it's offset a little bit, it's not going to be as favorable. If it's perpendicular, it's not going to be impacted, right? And if it's pointing in the opposite direction of my external magnetic field, right, this nuclear spin, then it might be an unfavorable interaction, right? And so the energy gained, or you know, kind of the stabilization or destabilization of a given state depends on the direction of this nuclear spin, right? Which is given again by the m sub I quantum number, right? The m sub I quantum number tells us about kind of the direction that spin has in a certain direction, in a certain axis. Okay. And so if we pretend we have some molecule, right, where I is equal to 1/2, right, then m sub I is equal to plus or minus 1/2. Okay, right? And so when there's no magnetic field, right, those are degenerate, same energy, okay? But if I apply a magnetic field, okay, then these energy levels are going to split, right, depending on whether or not it's plus 1/2 or minus 1/2, right? Okay, and so the splitting of the nuclear energy levels is then what we probe in NMR spectroscopy. Okay, so like any type of spectroscopy, right? What we're probing are energy gaps. Okay, well here we're creating the energy gap in the molecule by applying an external magnetic field, right? And then given that external magnetic field, I can probe this energy gap, right? And so that's what we do, right? We apply an external magnetic field, then you shine light on your molecule to induce a change in the nuclear spins, right? That induced change, right, is going to depend on the gap between the spin states in your molecule. And so we can probe that energy level between the different spin states, and then that can give us some information about our molecule. Right, and so, and often what we're probing in NMR spectroscopy is something called a chemical shift. Okay, and so what this is referring to, right, is right, the energy equation I gave before, right, depends on the external magnetic field here, B naught, right, but right. The magnetic field that's actually felt by the nucleus is going to be different than the external magnetic field because that magnetic field, right, has to go through the electrons before it can reach the nucleus, okay? And those electrons that are surrounding the nucleus will interact with that magnetic field and sort of dampen its strength, okay? And so these electrons, right, essentially are screening the nucleus from the magnetic field, right? Right, if you think about kind of in general chemistry, we learned about effective nuclear charge, right? That your valence electrons don't feel the full Coulombic attraction to the nucleus because there are core electrons in the way that are, right, that have opposite charge, and so their negative charge cancels out some of the positive charge from the nucleus, so the valence electrons feel less of a positive charge. Well, that's the same thing with the magnetic field reaching the nucleus, okay, right? That the electrons are shielding the nucleus from the external magnetic field, right? And that shielding is what we'll kind of refer to as this chemical shift, okay? So sigma here, sigma is this chemical shift that we often talk about when in NMR spectroscopy, okay? And it's basically how much is the external magnetic field reduced by the electrons, right, to produce then some local magnetic field, okay? around the nucleus, right? And so this chemical shift, sigma here, right, it depends on the electrons, right? It depends on the electrons, your electronic state, right? It depends on that electronic wave function and things of that nature. So how large the shift is very much depends on the state in the environment of electrons, which can tell us some information about your system. Okay. Right. And so we can kind of talk about some general trends about this, and then in the next video on NMR, we're going to talk about NMR spectra and interpreting these things and so on. Okay. So before we do that, right, we'll just talk about some trends, right? So first off, right, how do you expect the shift to change with increasing or decreasing electron density, right? So if I imagine I have some sort of nucleus, right, and I have some amount of electrons floating around this nucleus, right, do I expect the shielding of that nucleus to increase or decrease with an electron density, right? And we'd expect it to increase, right? The more electrons I have around here, right, the more difficult it is for that external magnetic field to reach the nucleus, right? So with an increasing electron density, I'd expect an increased shift, right? An increased chemical shift, right? Similarly, with the decreased amount of electron density around my nucleus, I expect a decrease in the chemical shift, okay? Right, and there are other things besides just the electron density around the nucleus. Things like the solvent around the molecule can impact, right? And because the solvent itself can have some amount of angular momentum, orbital angular momentum, things like that, and it can generate its own magnetic field, which can affect then the external magnetic field strength that reaches your nucleus. Okay, and things like aromatic rings can also help shield or de-shield the nucleus, right? If I imagine I have a benzene ring, okay, right? You can imagine kind of the electrons in this benzene ring are circling around the ring, right? And they're going around and around and around and around and around, right? And so that circular motion of the electrons is generating a magnetic field, because again, moving charges generate a magnetic field, okay? And so this benzene ring has an inherent kind of magnetic field it can generate, and so it can have a very large impact on chemical shifts of nearby atoms and other things like that if this benzene ring's in the way of the magnetic field. Okay. All right, and so that's going to be it for kind of this video, right? We're talking about chemical shifts and what is NMR spectroscopy. In NMR spectroscopy, we're inducing energy gaps in our nucleus by applying an external magnetic field, right? And the strength of that magnetic field that reaches the nucleus is reduced by a chemical shift, okay? Which is often what we kind of report and study for a lot of molecules.